Okay, so let's start. Today there is not going to be too much C++ in this first section. Actually, I'm mainly going to be talking about data-oriented design, which is kind of a way to organize your code. And this is going to be important for us in order to leverage the modern memory hierarchy of modern systems as much as we can. So let's dive in. And let's start with a little motivation as to why we even care so much about memory layout and data-oriented design. So if you go back to '98 and you look at the CPUs and the associated memories on the market, then you can see that the CPU was running at 400 megahertz, and it had the first iteration of DDR memory, and its output was less than 1 gigaflop. So, yeah, I think I'm missing a G there, but they're supposed to be gigaflops. No. Sorry, wrong table. Yeah, so you can see that it's got 0.2 gigaflops of performance. If you don't know what flops is, it's basically floating point operations per second. You can take FMA or just multiplication or addition, whichever, it doesn't matter, like in the big picture. Because if you look at the CPU from last year, then you can see that it's got 16 cores instead of just one. And instead of running at less than a gigahertz, it's running at 5 gigahertz. And on top of that, it's got 16-way SIMD. So instead of doing just one floating point operation per a couple of clock cycles, it can do 16 at a time. So if you do the math, you can see that it's got more than 1 teraflop of performance. If you look at the column next to it, then the bandwidth of the memory hardly changed. I mean, it didn't even change from gigabits or gigabytes per second to terabits per second. So if you check the ratios, then you can see that the performance of memory, that is its bandwidth, grew 30 times over this 25-year period, whereas the performance of CPUs climbed a whopping 6,000 times. So the consequence of this is that today the CPUs are much more powerful in comparison to memory. And because of that, oftentimes the bottleneck in today's applications is the memory, not the CPU. So the CPU could do more and more calculations, but you just can't feed it because the memory is too slow. So today we are going to learn about techniques that help us leverage the memory better, more efficiently, so that we can actually feed the CPU with the data that it can process. So a bit of an introduction to data-oriented design. Like, what is it actually? Usually people contrast it to object-oriented design, which makes sense, because if you think about object-oriented design, then you usually think in terms of objects. So you have a class for this, you have a class for that. It's very convenient because this is how people think, this is how we interpret the world. So it's convenient for us to understand, but it's not so convenient for the machine to process. So when we talk about data-oriented design, we try to arrange our code so that it's easy for the machine to understand, and hopefully it's also easy for us to understand. So to make it easy for us, there are some ways to kind of think about this. So first of all, you don't think in terms of objects, but you think in terms of transforms. So, like, if you look at the slides, like on this picture, like you have a multiplication here. That's a transform, like you multiply two numbers. And you think about the transform itself, not so much about the data that it uses. And then you can basically make a graph. It's a bit like, for example, an inheritance graph of objects, but instead you kind of have a data flow graph or data transform graph with many transforms along the way. And once you have that laid out, you can also tell what the inputs and the outputs to these individual transforms are. So for example, in order to calculate accelerations of particles in a system, you would be dividing the forces by the masses of the particles. And once you kind of thought this graph out, like how you're gonna get your end result, which is the new positions of the particles in, for example, an n-body simulation, then you can think about how you're going to lay out your data, that is the input and the output to your transforms. And of course, you want to lay out your data in a way that is efficient for your computer system to read in and write out. So basically, when we compare it to object-oriented programming in a bit more concrete fashion, like through this Embody example, then your starting point is roughly the same. Like you think, okay, I'm going to need an Embody simulation, so I'm going to make one. But when you go with OOP, you're going to think, so Embodies, let's have a body class. And since it's OOP, you're going to be adding methods to that class, like calculate the force on the body. And then once you've got all your bodies, you're going to encapsulate them into a simulation class that's going to have an update method and so on and so on. When you do data-oriented design, you pretty much start with the same thing because it's just the definition of the problem. Let's make an Embody simulation. But then you start thinking in terms of transforms. So like, yeah, not a body class, but let's have a function, a transform that calculates the pairwise gravitational forces between the particles. And then you think about, okay, what sort of input does this pairwise gravitational forces algorithm need? So you define those inputs as well. And at the end of the day, you lay your inputs and outputs out in memory in a way that's efficient for the system to read. Which leads us to basically the rest of this presentation. What is efficient from the system's point of view? Now, a bit of theory on the memory hierarchy of modern systems. I'm sure you heard about all these terms, but it's nice to have them on a table where you can see the general trends between these different kinds of storage systems. So like at the bottom of it, which I did not even put, sits the good old hard drive. Well, it's very slow, but today we've got SSDs and they're quite fast. So today SSDs can put out 7 gigabytes per second of reading speed and a bit less writing speed. And PCIe 5 SSDs are even faster, like 11 gigabytes per second. That's like in the same, like almost in the same league as DRAM. However, SSDs still have quite a bit of lag. So if you request data from an SSD, you're gonna have to wait like 4,000 or more CPU cycles. And that's not very good because in those cycles, your CPU can't do anything useful. So if you step it up by a notch, then we have the DDR5 RAM, and that's a lot faster. So like one module can do like 40 gigabytes per second, and then you can also have 4 channels on a server, for example. Its latency is also a whole lot better, just in the order of 300 cycles. And then we've got 3 levels of cache. This is memory that's built into the CPU. This also doesn't work the same way as NAND flash or RAM. This is static RAM, so it's basically just silicon, no capacitors or whatever. And if you look at the table, then you can see that the latencies and the bandwidths of these caches are very high. And then at the top of it, we've got registers. I mean, registers, the bandwidth is basically infinite, and the latency is 0 because CPUs can only do operations on registers directly. So like adding 2 locations from memory doesn't work. Adding 2 registers, yeah, it does. Now the trade-off is the higher you go in the table, the pricier these things get, and also the more power they consume. So you can just be, okay, I'm gonna have 1 terabyte of L1 cache. It's limited to fairly small quantities. So first, yeah, that's a bit like drifting. So first, let's talk about the operation of DRAM, because in order to use it efficiently, you kind of have to understand how it works. Now, unfortunately, the organization of modern SDRAM is very complex, and well, I have to admit that I don't fully understand it either. But the good news is that we don't have to. Like, a simplified view of the whole thing is enough for us. So going through the reading procedure is going to help us come to some conclusions. Now, how do you read from DRAM? So first, you have to set the address to the DRAM that you want to read. And then the DRAM is going to do some processing. And in the meanwhile, you just wait. That is, the CPU is just waiting while the DRAM is preparing to serve the memory to you. And finally, once the waiting is done, you get, say, 64 bits of data from the DRAM. And you can just like read that out from the pins of the memory module. And once that's done, you can just move on to the next address. And one thing to remember about the next address is that when you set the next address to the DRAM, if it's close by to the previous one, it usually starts serving the data to you pretty quickly. But when it's very far away, then you have to do the waiting again. So, conclusion, of course, you want to read pieces of memory that are close by to each other. And this is especially underlined by the so-called burst mode of DRAM. So remember, I just told you that you get normally 64 bits of data once you do a read from DRAM. But DRAM can do a bit more than that. It's got a lot more data available to you, and it could serve it if you wanted it. And in fact, this is what always happens basically in today's systems, that instead of just one chunk of 64 bits, you get 8 chunks at the same time. Well, that is not at the same time, literally, but like in quick succession. So between these 8 chunks, there is absolutely no waiting. So you basically always get 8 times 8 bytes of data. And this leads us to our first lesson today by using DRAM efficiently. If you just request 1 byte, you always get 64. So why not use all those 64 bytes? So think about this example. How do you use DRAM poorly? These would be the memory cells that you have. Say each of them is a 64-bit int. And what you're trying to do is access every 8th of them and just add them together. So say you access this one, then the DRAM gives you a burst of 8 pieces, and then you get all these guys as well. But you just don't use them because that's not what you want to do. You want to sum every 8th of them. But on the other hand, you could just also sum up the whole array, right? If you have a massive array. And in this case, you basically process every single element and you try to add them up. Now, if you look at the example code, it's not very important. I think the picture is better describing the situation. It's using a pairwise sum to sum up those 8 elements. So it goes 8 by 8 by 8, and it uses a pairwise sum on the 8 elements. This is important because modern CPUs have multiple lanes for doing integer arithmetic, so it can do perhaps up to 4 integer additions at the same time instead of just 1. So when you do a pairwise addition, then the first batch of 4 operations are done at the same time. And the second one, of course, you have to wait for the results of the first batches. But that can also be somewhat parallelized by the CPU. So, I have a question for you. If you think about these algorithms, like summing every 8th element or summing all of the elements, and you give them the exact same number of items, say, like 8 million items, that means that the first algorithm, summing every 8th of them, is going to touch only 1 million items, but the second one is going to touch all 8 million items. Now, given this, which one do you think is faster? The first one, where you sum only every 8th element, they're equal, roughly, in runtime, or summing all elements is faster? So, who's voting for 8 elements, like summing every 8th is faster? Put your hands up. Nobody, okay. Who's voting for equal? Hands up. Good. Who's voting for all elements faster? Oh, interesting. Okay, so let's see the results. Now, of course, your mileage may vary. This is just on my system. And if you look at the timings, then summing all elements takes just a bit more time. Not too much more, but just a bit more. So I also calculated the memory bandwidth, the effective bandwidth. So when you're summing all elements, I got about 38 gigs per second being transferred from the memory. But when I was summing every 8th element, I got only like 6 gigs per second. And my computer's theoretical maximum is like 53 gigabytes per second. So you can clearly see that it is mostly memory bound and not CPU bound. So the answer, well, that is at least my answer to this question, is that they run roughly in equal time. Well, yeah, okay, you can say that summing all is a bit slower, and that's probably because we were already saturating the CPU with all these integer additions. But I'd say that's still like roughly negligible. So yeah, it's quite interesting that if you use all the memory, you're just as fast as if you used only like a small fraction of it. Because of the bursts, all of it is just pulled into the caches. So yeah, the takeaway is fairly simple. Like, you can't read just 1 byte, you always get 64 bytes, so try to make use of it. Okay, I don't know why this is drifting. I don't think I have any control on this to change it. Yes, okay, so this is a slightly different test. So say we allocate a massive chunk of memory and we split it into blocks of equal size, and then we read bursts of memory from each block, and then we change the block. So like this, like the blue would be 1 block, and this reading number 4, that would be reading 1 burst. So 1 little cell is 64 bytes. So we can do multiple things, like we can shuffle the reads within a block, or we can read it contiguously. And ultimately the idea is that the whole array is so large that we are never actually using the cache. And also the individual blocks, so like the green from the brown is like essentially infinitely far, so you don't get any like interactions in the caching or the memory controller between these blocks. So yeah, as I said, the whole thing is large enough so that you never read the same piece of memory twice. And one thing to know here is that I was also doing some prefetching, because when you shuffle stuff, so when you take a block of 16 burst sizes and then you like shuffle the reads inside it, then the CPU doesn't really have an idea which one you're going to read next, and it needs a little bit of help to figure that out. So prefetching, we are going to talk about that later as well. This was essentially needed to get the results that I wanted. So let's look at the bandwidth that we get, like in the 2 scenarios with the different block sizes. So you can see that when you do sequential access to the memory, that is, in these blocks, instead of like the memory is crossing each other and going all around, you get some nice linear sequential reads. Then our performance, our bandwidth dramatically increases as we increase the block size that we read from. Whereas with randomized reads, it's a bit more tricky. So somehow, like with very small blocks, you get a poor performance. With middle-sized blocks, you get a somewhat decent performance. And with very large blocks, it's bad again. Now, if you think about it, when you have tiny blocks, then you do like 2-4 reads in there, and you jump to a completely unrelated memory location. As we just discussed, when you jump far in the next address that you're reading, your performance is going to be poor. And this is exactly what's happening. Small block reading like 4 bursts and then you jump far away, your performance is going to be bad because you jump around a lot. Now, if you have a middle-sized block, say, I don't know, 128 elements, and then you do your random reads in that block, then you're still kind of staying localized, not as good as sequential access, but you're more or less still localized. And that's when you get peak performance. When you have a very large block, then again, you get a completely random behavior, just jumping all over the place. And the DRAM has to do a lot of work to serve you the data, and you have to do a lot of waiting to actually get that data. Now, I think the graph for randomized access is not very useful. You just don't want to do it anyways, because if you look at sequential access to memory, it's just base randomized every time, even if you work at the peak of randomized access. Yep. Yep, so let's move on to the cache hierarchy of modern CPUs. On some of the first slides, I already mentioned the L1 to L3 caches, but this is a bit more information about them. So the typical size of these caches, first of all, like L1 is very fast, but it's also very expensive and power hungry, and as a consequence, it's also very small, so you typically get 32 kilobytes of data cache and 32 kilobytes of instruction cache. Yeah, it's split in two, so one of the caches only stores the instructions, and the CPU fetches like AVX vectorized float add and things like that, whereas the other one actually stores the data that you have. Then you move on to L2 cache, which has got the size of about 1 megabyte. And then you move on to L3, which is these days 32 megabytes, even perhaps up to 100. Now what's interesting here is that the L1 and L2 caches are tied to a processor core. So each CPU has its own dedicated L1 and L2 caches, but the L3 cache that is shared across all CPU cores. So if you want to work with the L3 cache, the CPU cores somehow have to synchronize. And the same goes for DRAM, of course, but it's shared between the CPU cores. But DRAM is always accessed through the L3 cache, so that doesn't really matter to us. Okay, so now we know how the caches are organized, their properties, sizes, speeds, and so on. But how do you actually use them? Like, how do you get a piece of data from DRAM into a register? Because remember, data from DRAM can be used, it has to be loaded into a register, and you have to do that somehow. So there is a procedure for that. First of all, you check if the data is in the L1 cache of the CPU core that requested it. If it is there, then it's good. Just load it into the register and you're done for the day. But if it's not there, then you have to check the L2 cache and then the L3 cache. And if not even the L3 cache has it, then you have to actually go to the DRAM, tell the DRAM the address. Okay, I want to read from here. Then you have to do all the waiting. And then finally, your DRAM is going to serve you the data. And then you're going to take that data, insert it into the L3 cache, insert it into the L2 cache, and then finally to the L1 cache. And finally, from there, you can put it in the register. So it's a fairly involved procedure. Now, of course, when you insert data into many of the caches, like it might happen that the cache is full. And in that case, you have to check out some data. There is several algorithms for that. It's not very important to know how they exactly work. It's just that you make space in the cache. Now we have two terms that we often use when talking about performance analysis. One is a cache hit. So a cache hit happens when you request an address, and it is actually found in the cache, so you don't have to go any further, potentially to the DRAM. That is called a cache hit. Now you can have different types of cache hits. You can have a hit in L1, you can have a hit in L2 or L3. Of course, the best is when you have a hit in L1 because that's going to incur the least amount of delay. And then, of course, the opposite of a cache hit, a cache miss, when you don't actually have the data in the cache yet, so you have to go all the way to the DRAM and fetch it from there. And we don't like cache misses, and we do like cache hits. So writes, unlike in the case of DRAM, because for DRAM it's reading and writing pretty much the same, but with caches it's a bit more complicated because of the multi-core systems that we have today. So writing into the DRAM through the caches is usually pretty simple, actually. So you just take the data that you have in the register and you put it into the CPU's, like your local CPU core's L1 cache, and you call it a day. It's done. Like, you don't need to write it to L2. I mean, why would you? That takes a lot of time. Why would you write it into DRAM? That takes a lot of time. You just put it into L1 and call it a day. So now the question is, since L1 is pretty small, like, how does the data get to the DRAM? Because, well, at some point it has to get there, right? So basically, when you put that little piece of data into the L1 cache, preparing it for being written into the DRAM, you don't actually do the writes, but you flag that little piece of data in the L1 cache as something that is like newly inserted there. So when somebody else goes into that L1 cache, puts something else in there, and there is not enough space anymore, and the data that you just flagged as new has to be evicted from the cache. This is when it gets written back to L2 cache, and the same goes for L2 and L3 caches. If it has to be evicted, then it always gets written back to like one level higher, which sometimes even like gets written back to the HDD or SSD if you're using swap files or page files. So we talked about putting data into the L1 cache and like other caches, but what is this data exactly? So it's organized into so-called cache lines. Now, a cache line is basically just a block of data. So there is no such thing as putting 1 byte into the cache. You can put either a full cache line or nothing. So what this means is that a full cache line is 64 bytes. You divide your entire memory space into 64-byte blocks, and those are going to be your cache lines. And some cache lines are going to be resident in L1 cache, some in L2, some in L3, some, well, just in DRAM. Of course, with each cache line comes some metadata, like you have to remember what the address of that cache line is. So like, it's okay that it's in L1 cache, but what are you actually storing there? So you have to know the original address where it came from. And then, as we briefly mentioned, you can have this like flags. You can have these flags, like this data was just put there right now and it's new, and if you evict it, you have to write it back to the DRAM. So basically, the data itself, its original address, and all the associated flags. And now, how do you evict data from cache or so-called replacement policies? There are many strategies and complex implementations and all that. Actually, I don't really care so much about it. It's enough to know that the most common or most practical way of dealing with this is using this least recently used algorithm. So you're just going to evict the data that has been there for the longest time. Ultimately, or like ideally, you want to evict the data that's not going to be used anymore, but you can't tell that, so you can't see into the future. So you're just going to check out the one that hasn't been used for a while. Now, cache coherence. So in modern CPUs, you have multiple CPU cores, right? So imagine like both of them write the same address. they just put the values into their own L1 cache. So now you have two copies of the same address, the same piece of data. That's kind of a conflict, right? So which one is actually the true data? So somehow the multiple CPU cores of a system have to synchronize. And this is called cache coherence. Like your system can be either cache coherent or non-cache coherent. Most systems are cache coherent, even if you have NUMA. Yeah, I think what's important to mention here is the basics of this process, of this synchronization process. So imagine one thread on one CPU core puts a piece of data into its own L1 cache, and another CPU core on another thread requests that same address. Now, it's only resident in the L1 cache, not in the DRAM or in the L3 cache, the closest things that actually share data between the CPU cores. So somehow, one CPU core has retrieved the data from the other CPU core's L1 cache. And that is a bit more of an involved operation. It also takes a lot of time, so you kind of want to avoid that situation. But yeah, basically, as you perhaps guessed, what happens is that when you request another CPU core's L1 data, then it has to be written back into L2, then it has to be written back into L3, and from that L3 cache, which is shared across all CPU cores, the other core can finally retrieve that piece of data. Now, the practical implementations of this, like how do you actually do this in Silicon? Well, I guess it's complicated, but it's enough if Intel and AMD and ARM knows it. Okay, so let's do another test. Let's try to see how the caches work. We're going to start by allocating a memory block of a certain size, and we're going to keep reading that block repeatedly. So this is unlike the previous test that we have done. In this case, the memory block is going to be fairly small, so that it actually fits into the caches. Not like so big that we don't benefit from the effects of caching at all. And we're going to check the performance based or like in function of the size of the block that we are reading repeatedly. So imagine this is allocated in a std vector and just go through it again and again in a quasi-infinite loop. And we're going to measure the bandwidth of the data acquisition. So I think I put this on a graph, and it's quite interesting to look at. So where should we start? Maybe let's look at this section. So you see that this part of it is quite flat. I'm not that tall, but the part is also quite flat. So you have these flat regions, and in between the flat regions, you have massive drops in performance. This is essentially the point where the data, your block, gets so big that it doesn't fit in that cache anymore. So the rightmost part, like this part, is when you're not using caches anymore because your data is just so big that it doesn't fit even in L3 cache. And in this case, if you look at the side, then you get like 40 gigabytes per second of memory bandwidth. This is the number that we have seen so far in the other tests as well. That is essentially the bandwidth of the DRAM of the system that I had at hand. But once your data is small enough, so like 64 megabytes for me, that it fits into the L3 cache, then your performance increases drastically up to 120 gigabytes per second. And once again, when your data gets even smaller and it fits into the L2 caches of the CPUs, then your performance jumps up again. And I think at that point, like 140 something, 150 gigabytes per second, I think we're not actually limited by the performance of the cache, but the CPU is just not being able to keep up with all the computations. In fact, this is kind of also like hinted by the fact that when you switch from L2 cache to L1 cache, you don't see any difference in performance whatsoever. So probably the CPU just can't keep up with the calculations anymore. So what does this graph tell us in the end? Basically, you want to always keep your data in the smallest cache possible. You want to have your data that you actively work on all put into the L1 cache or into the L2 cache. Or if you can't, at least into the L3 cache. If your data is all over the place and it doesn't fit into caches, then your performance is going to suffer. Now, false sharing. Remember this cache coherence thing that you have to like synchronize between the CPU cores. And also, we talked about cache lines before. So you can't just put like 1 byte of data into the caches. You always have to put these 64 bytes of data in there. Now think about it. You take a 64-byte block, you change like 1 byte in it, then the whole cache line has to be updated. Now another CPU core requests some data from that same cache line, but not that data that the previous CPU core changed, but something else. So in that case, that cache line has to go again to L2, L3, and then back to the other CPU core's L1 cache. So the two CPU cores essentially are just playing ping pong with that cache line. And in reality, they are not even sharing any data between each other. So this is why this phenomenon is called false sharing. So basically, you want to make sure that the different pieces of data that your different threads work on don't fall into the same cache line when they don't have to. So when the CPUs don't actually need to share the data between each other. And okay, so I also wrote a little test for false sharing. I don't think I need to explain the method. The idea is that, well, maybe I have to. So the idea is that I had like 1 to 8 threads that were basically hammering the same cache line at the same time, although they were not actually hammering the same exact bytes, just bytes like right next to each other. And then I measured the performance of such an application. And what you get is basically, if you don't have any false sharing, then the task finishes in like 180, 160 milliseconds all the time, regardless of the number of CPU cores. Now, this is because like you would expect normally some scaling with the number of CPU cores. Like 2 cores work faster than just 1, right? Because they're doing some simple logic like adding numbers. 2 cores can do it faster. But the thing is, it's already limited by the memory bandwidth. So chucking more cores on it doesn't change anything. Like your memory can't keep up with any more than 2 cores. So no performance speed up for you. The only bump in performance that you get is when you switch from just 1 thread to 2 threads. Because apparently just 1 single CPU core, like it was saturated with arithmetic operations and the DRAM could easily keep up. But now, when you have false sharing, that is, the CPU cores hammer the same cache line, but they don't actually share the data between each other, your performance decreases drastically. So, like the worst one is 8,000 milliseconds versus 160 milliseconds. And all this performance is lost basically in ensuring that the cache stays coherent. It doesn't contribute anything, like all these operations don't contribute anything to your application. So that's why you definitely want to avoid false sharing and think about cache lines. And when your data, like different pieces of data, go into the same cache line, then you should sound an alarm and do something about the situation to improve performance. And as I previously mentioned, there is this thing called the prefetcher. Now, if you go back to like the first couple of slides, I mentioned that you have to wait a lot for the DRAM. Once you specify the address, you have to wait a lot until it actually serves you the data. So like what happens if you read pieces of data consecutively from memory? Like you said, the first address, you have to wait a lot. Okay, you said you got your data, you do some processing. You said the second address, you have to wait not a lot, but still some. Because, well, you set a nearby address, so you don't have to wait so much, but you will still have to wait a bit. And you wait that bit, and then you get your data, you do your processing, set the next address, wait a bit again, then get the data, do the processing, and so on and so on. It would be nice if we didn't have to do any of this waiting between the pieces of data that we get. That's why the CPU has this so-called prefetcher. Now, we can talk about software-guided prefetching and hardware-guided prefetching. So when you do hardware prefetching, the CPU is basically doing a guessing work. Like it thinks, okay, this application has requested data bank 1, 2, 3, 4, 5. Well, I guess the next one is gonna request data bank 6. So even before the application actually like sends its request, the CPU is going to go ahead and just fetch that data into the L1 cache. So when the application finally gets to the point where it's done all the processing and it wants more data, then the CPU can be like, okay, this data is already in L1 cache. I'm just going to give it right away to the application. So this is what's called prefetching, or well, hardware prefetching to be more specific. Now you can also guide the CPU in how it's doing the prefetching, because there are these prefetch instructions. It's basically like mov or add or mul. It's just an add instruction. You give it an address as an argument, and then the CPU is gonna be prefetching that piece of memory. So just put this into the instruction stream of the CPU. And when is this actually useful? Manual prefetching. Like, for example, in the example before where we had the random accesses, the CPU has no way of guessing which one you're going to read next. But I was actually just feeding it a stream of prefetch instructions because I knew exactly what the random number generator is going to give me next. So I could tell the CPU which pieces of memory to prefetch. Yep. And how do you use the prefetcher? Because obviously you want to use it. Now, of course, there are two ways to make use of the CPU prefetcher. One way is to kind of play the data into the hands of the prefetcher, into the hands of the hardware. So you just do simple, easily predictable sequences of memory reads. For example, just sequential access like 1, 2, 3, 4, 5, so on. You can also do like negative accesses like 5, 4, 3, 2, 1, whatnot. You can also do jumps, so like 0, 4, 8, and so on. Like the CPU is pretty good at predicting these simple patterns, sometimes even more complex patterns. And ideally, you want to make use of that. If you can't, for some reason, you have a very complex data structure. I don't know, like you have a tree, for example, like a binary search tree, then you expect the next nodes of the tree to be accessed while you're accessing the current node. Maybe you can manually issue a prefetch instruction to the nodes below in the tree. And then by the time you actually visit those nodes, they're all going to be in L1 cache. So you can also use manual prefetching if needed. But I don't have like any benchmarks or this, but be warned, the internet said that using the manual prefetcher can interfere with the hardware prefetcher, and you can also just put too much crap in the caches, effectively negating their help. So be careful with manual prefetching, but use it if you have to. So these are eventually the same graphs that I've just shown you about the sequential and randomized x-axis versus block size. If you look at the blue graphs, they are literally the same as the ones that you've seen before. Now, the only difference is that I also added the yellow or orange graphs. And with the orange graphs, I disabled the manual prefetch instructions that I was supplying the CPU with. And basically, you can see a substantial drop in performance. So when you have sequential accesses, this performance drop is not actually that severe, but still a couple of %. Now, this is not to say that if you have sequential accesses, you should be using software prefetching like crazy to get those extra 2 gigabytes per second. Usually this is not going to be a problem for you. The CPU prefetcher does its job fairly well, so sequential accesses, avoid using software prefetching. But for randomized accesses, you can see a much more substantial drop in performance, basically about 60% drop. Well, that is, you have to do a bit more math than that. 30% drop and 60% gain. So a substantial difference between the manual prefetching and without the manual prefetching. So in that case, if your memory access is not very predictable, then you're better off using manual prefetching. So let's talk a bit about how to actually leverage C++ to do proper use of the memory. Because so far it's only been like theory that you can kind of apply in any language like Fortran, whatnot have you. So yeah, the first thing that C++ gives you now in the standard is over-aligned memory. Normally, each piece of data or like each data type has its own alignment. So like a double, if you have a double that's aligned to 8 bytes, that means that the lowest 3 bits of its memory address are always 0. So its address is a multiple of 8. In other words, floats are aligned to 4 bytes. Characters are aligned to 1 byte. Usually it's the same as the size of the data type. But sometimes you want memory to be over-aligned. This can be for communication with hardware, to better interact with the GPU's caches, or most commonly in the case of CPUs for SIMD types. So if you have AVX or SSE, then those vector types usually require a higher alignment. So when you have an AVX type, so like 8 floats plugged into a vector, that's 256 bits, then you're going to have to use an alignment of 256 bits. And with C++, you can use the align as keyword. Align as takes, do I have an example? Oh, I actually do. So align as takes like an integer constant. So in this case, I don't know, 256 bits switched into bytes. And then you can use that number to specify the alignment of a certain type. So if you want to make an SIMD vector type, you're just going to be like, okay, let's have a struct. It's going to have members X, Y, Z, and W or something. Or they're going to be floats or doubles, whatever you like. And then you can specify the align as on the size of the, on the declaration of the struct. So like you say align as whatever 16 vector 4. But you can also put the align as on variables. So like you can just specify the alignment of the elements of the vector. And then the whole vector itself is gonna respect that alignment as well. Now there is also another keyword, align off. Align off can be used to query the alignment of a certain type. So if you include the Intel intrinsic headers for like AVX or SSE, then it already has some types declared for you. And if you want to know the alignment of a certain vector type, then you can just use the align of keyword. So it basically works like size of, but it doesn't give you the size, it just gives you the alignment. And how do you typically use align of? You query the alignment of a certain type, and then you pass it to an allocation function, which is like malloc, but it aligns align memory. It's called std aligned alloc. Now, unfortunately, this function is not supported on some compilers, notably MSVC, so that's kind of unfortunate. Even though it's in the C++ standard, you can't really use it without if-defs. And also align of can be used with operator new and operator delete. Actually, you don't kind of use it directly, but you just pass an over-align type to operator new, and it's gonna magically know the alignment of that type. That is if you use C++ 17 and above. If you use something below, then you might run into surprises. Now, why is alignment important? These days, it's not that important actually, at least when talking about SIMD and CPUs. But back in the days, we had two instructions to fetch a vector from the memory. We had an aligned load and an unaligned load. And on some CPUs, the aligned load was actually faster. So you always wanted to align your SSD registers in memory to their proper alignment, so that your reads would be faster. These days, most of the time you just don't care because the CPU is just as efficient with aligned and unaligned loads. Well, they're close, so you just issue an unaligned load and call it a day. And yeah, so here we see examples for both. This vector type, this vec4, with its alignment of 16 bytes, could be used as an SSE type. And in fact, the second example shows just that, loading this vector4 into an XMM SSE register. And as I said, you can use the aligned version, which is the load PS, and the unaligned version, which is the load UPS. And as I said, you can also just allocate basically an array of vectors, and it's going to do, like operator new is going to do the alignment for you automatically. Now, cache lines. So I told you that cache lines are 64 bytes. Well, this is not always the case. I mean, on x86, yeah, and I think probably on ARM as well. But you can't just assume this for granted. It doesn't have to be 64 bytes. In fact, it doesn't even have to coincide with the burst size of the DRAM that it's operating with. And C++ helps you with these two sort of helper constants, hardware destructive interference and hardware constructive interference. And these functions essentially give you the size of the cache line. So destructive interference happens, like in the example that we've just seen, that your runtimes basically just blow up because the CPU threads are interfering with each other in a destructive way. And the hardware destructive interference function of C++ gives you the minimum offset between two pieces of data, such that they don't cause this false sharing that makes your performance suffer. And hardware constructive interference is kind of the opposite, when you actually want to have the data so close that they are fetched in the same cache line all the time. So that gives you the minimum offset between, it gives you more like the maximum offset between the two ends of the data bits, data pieces, such that they still belong to the same cache line. Now, again, it's a bit unfortunate, but these functions are also not supported in all systems. Notably, it's not supported in libstd C++. So if you're using GCC, perhaps CLang, you're out of luck. I don't actually know if it's supported on MSVC. Maybe, maybe not. So again, just like with aligned alloc, you're going to have to fall back to if-deffing the cache line size is to 64 bytes, because that's your best guess that you have. Yep. So now we've been talking a lot about data-oriented design and why it's important and how we want to squeeze maximum performance out of our memory chips. And some people have gone so far on the internet, if you search for data-oriented design, they're going to be like, okay, object-oriented programming is dead and long-live data-oriented design, so now let's do everything with data-oriented design. Well, I'd advise a bit of caution when reading these articles and watching these YouTube videos, because data-oriented design is just another tool in your toolbox. It's not something that's going to solve all your problems. It's not something that's going to make all your code beautiful. So use it with care. Just be aware of it and use it when you need it. So the common questions: can you still use OOP? Yes, of course. I mean, as I just mentioned, this is how humans normally think. Not machines, but humans at least. So when you organize your code using OOP, chances are that if somebody or future you goes read that piece of code like sometime later, they're actually gonna understand what you meant, and that's a huge advantage. So yeah, keep using OOP. It's very intuitive and very helpful in making clean code. The other question is, when do you not use OOP and when do you use DoD? So sometimes you notice when doing profiling or just thinking about how your code is actually using the hardware, you sometimes think, well, okay, this OOP code is nice, but it's very slow. So perhaps you want to rewrite that in a data-oriented design, leveraging the full capacity of your hardware. But it has to be justified. In other cases, though, interestingly, data-oriented code is nicer than OOP because it expresses your intent clearer. So you can also use data-oriented design purely for cosmetic purposes. Well, okay, you'll, of course, get some performance benefits out of it, but sometimes it helps with clean code as well. And the third question, when it comes to the two paradigms, can you mix them? Yes, well, basically you can. I mean, normally the way you would have this is that you would have a data-oriented layer at the bottom of your code organization, and above that you would have a wrapping OOP layer that would make management easier. Were you going to say something?
Yeah, a comment. I think.
Where have we got one?
Okay.
Does this work?
I think, at least in my experience, the object-oriented design fails a bit in that sense, and it's a bit at odds with DoD, just when you focus on two small objects. If you take as object something larger, then things work. If you, for example, we will have an example in the exercises, but if you focus, for example, on a single particles as object, you have issues. Whereas if you focus on the whole system or groups, and so where you have always groups of particles and so on, then there is less tension between the two.
Yes. So basically, this is my last slide. So the closing remark is performance and readability are kind of different metrics, and you usually strive to be the best in both. Sometimes you have to do trade-offs and trade some clarity for performance, and sometimes one method of programming helps you with achieving either of your goals. So pick wisely and use the tool that best suits your needs. Now, I also have some references. I don't think these are very useful to you unless you want to dive deeper into this topic. Yeah, but one thing that I would actually highlight for you is, I can't reach that high, but it's the link with agner.org. And so this guy, I think he's a Danish guy, and he's got this very useful instruction tables PDF. And basically this table contains the latencies and the throughputs of all instructions for pretty much all CPU architectures out there. So if you want to know how long an SQRT, like a square root, or how long a multiplication or a vectorized add takes, then you can just go to that table and check it out. And this is going to help you doing calculations regarding your memory bandwidth needs and how fast your CPU can actually do data, or how you want to overlap certain operations, like reading a piece of memory while your CPU is doing a complicated square root calculation, or interleaving integer arithmetic with vectorized arithmetic, and so on and so on. Rest of the links, not that useful. I mean, there are some which, like the one that the cursor is on, I think that one is quite good in describing how DRAM works in detail. So if you want to dive in, just go for it. And finally, I don't know if you already know, because I kind of missed the previous lectures, because I was working on the slides. But we've got all the slides and all the source code on GitHub. So you can just scan this QR code, go to the page, and there you can access the full source code for all the examples that you've seen in this presentation. And by that I mean not just the code snippets, but like the whole thing that measures the performance of different operations. And if you want to, you can even run it on your own system and see what results you get, if you get the same graphs as I did or not. And that's pretty much it about data-oriented design. So thanks for your attention.